Swayam Prabha. Digital India. Educated India.
Happy to see you after 4 days. So it's very hectic. Saturday, Sunday, or only Saturday you have lectures. Sunday also? Not hectic too much. It's okay. And everybody will come and tell you that this is an important subject. Am I right? Everybody will say like that. End of the day, nothing, everything cannot be important. Am I right? Everything you need equally. Am I right? So when you make a some cooking item, some dish, if you like salt or sweet more, you cannot dump with that. Am I right? So you need everything. So you listen to everything, make a note, you will get a notes assignment, then you find out wherever you are lacking. Am I right? All of you are toppers. That's what I understood on that day. So your understanding supposed to be better than a normal student. So you try to grab, make a note, you may forget. Am I right? So whenever you need, you can just go through. That's the way Chittiram Kai Palakam. Am I right? Otherwise you will forget. Very simple. If you think that I am very sharp, clever, I will remember everything, that all will not happen. But if you read 3-4 times again and again, if you like some topic or wherever you are weak, then slowly you will remember. Okay. Good. I don't know whether you remember me or not, I don't know. So my name is Sekar. So presently head of the department. But I am here not as a head of the department. I am here as a faculty member in chemistry department, particularly in organic division. So I do research in the area of organic chemistry, and also I teach in the area of organic chemistry. So that's my background, and my research is mainly focused on asymmetric synthesis. So that's why I chose this topic, basics of asymmetric synthesis. Generally I give a particular topic where I do research, but this is all for the basics, am I right? So you will be trying to understand some of the subjects you are learning even better manner, or some of the new topics which are important in research stage. Okay. So I will be talking all about no research today, very little bit research, mostly basics of asymmetric synthesis. So how many of you heard about asymmetric synthesis? Raise your hands. Good. So you are just completed first year, going to second year. So asymmetric synthesis is the subject for the second year. Some colleges no, they don't teach, but they will teach you some reactions for sure. Sharp plus epoxidation. How many of you heard sharp plus epoxidation? If you don't know, don't need to worry, that they will teach you in the first semester. No need to worry. This is a little bit advanced topic in organic chemistry. So generally comes in the, but the basics for the asymmetric synthesis you study in not BSc +2, not even +2, +1, stereochemistry. Okay, that's what the stereochemistry is the basics for asymmetric synthesis. If you know the stereochemistry is good, then asymmetric synthesis will be very good. If you don't know the stereochemistry, then asymmetric synthesis of your knowledge may not be very good. So whatever I am going to talk is little bit from your +1, +2, little bit from your BSc, and definitely in the first semester MSc, you should have studied a separate topic called stereochemistry. Am I right? So mostly from there, and remaining half of the seminar will be slightly advanced. Basically, in IIT Madras, now we have a separate course, MSc, PhD elective course called Asymmetric Organic Synthesis. So that's the topic I have given, but it is only basic. Whatever the important topics we cover in full course, I will brief in 2 hours. Very basic. So wherever you don't understand, wherever you have some issue in understanding, you can feel free to stop, ask the question, we will explain, then we will go back. Okay. The question is, how important the asymmetric synthesis is. That is very important. No? If it is necessary, then only people will bother, irrespective of how important, how much needed. That is the most important question one should have. The first one, yesterday, journalism, right? When we do research in any area, the findings will be published. And where you publish depends on the quality of the journal, you get recognition. For example, the so-called journal called Nature, Science. Have you heard this journal name? Okay. If you publish today in Nature, you will become superstar the next day. Okay. Or you publish in Science, equally you will become superstar. That means that results are so important, so technically strong, something so new. That is for common journal. And if you go for chemistry specifically, of course, now we have Nature Chemistry, Nature Communication, and particularly more towards chemistry. Then you have a journal called Journal of American Chemical Society, JACS, or Angewandte Chemie International Edition, Angewandte Chemie. Okay. So, they are in chemistry considered to be topmost journal. You publish there, then also it is a very big news, very big news. If not, then you go to organic. Now I am coming to organic. So, if you take only two specific, so there is a journal called Organic Letters, Journal of Organic Chemistry. These are the important journals specifically to organic chemistry. So, what I did, so yesterday I took the Organic Letters current issue. Every week there will be one issue will come. So, this is the Organic Letters Journal 2025. Volume number 27. I mean every year that volume number will be this year 27, next year 28. This is a reference. You might have, we will see in my talk on several lectures, they will be citing the paper, am I right? This is the way to cite. Sometimes they will cite with the author name, but this is I am referring the whole journal. So, that issue has starting from 5546, 67 journals, papers in that issue. Out of that, 5 papers are asymmetric synthesis. Randomly I have picked up. I did not check which is having more asymmetric synthesis, which is having less asymmetric synthesis. I did not do it. So, I thought, okay, tomorrow I am going to give a lecture about asymmetric synthesis. I want to tell you with accurate data, am I right? How important? Just everybody will come and say that this is important, that is important, but reality. So, that is 7.5%. You take a volume randomly, in that 7.5% papers belonging to asymmetric synthesis. So, asymmetric synthesis is a branch. When we ask what is the branches of chemistry, so immediately we will say organic, inorganic, physical. Nowadays you include theory, sometimes you will use analytical chemistry, nuclear chemistry, am I right? So, like that we have 4 or 5 important divisions in chemistry. Now, you come to organic chemistry, that is the way it will go. Then you go to further organic chemistry, further, then you will be working in a tiny area and you have to do something which has not done by anybody. That is research, am I right? And that should be useful and you have to provide a solution for the unsolved problem. Then that becomes great research. So, in organic chemistry, so we can talk about catalysis, am I right? So many catalysts you see. Then if you talk about catalysis, then it is a big topic. My lecture on your last day, I have on the catalysis, nano catalysis I will be talking on that day. Or you can talk about developing reactions, we call it reaction methodology, is a separate topics. Synthesizing natural product, you know natural product? Can you tell me one natural product? Camphor, good. Anything else? Nature product. Is there name? Answer is there. Anything from nature is called nature product. Okay. Your glucose is a nature product. It is made by our body, no? Nature makes. So, there are compounds we can classify by 2 ways. Chemical synthesis, nature product. Made by us in the lab, made by nature. So, whatever nature makes is a nature product. Nature is great in the end of the day, am I right? That we will see. If you are making for some reasons, so that is man made. The technical term is chemical synthesis. So, nature product is made by nature. When nature makes, we call it biosynthesis. Whatever you, for example, you have cholesterol in your body, good or bad, that is a secondary. Without cholesterol you cannot live, am I right? Our body makes. How it makes? You have, do you remember cholesterol structure? It's a 4, it's alkaloid having 4, 5, 6 member, 6 member, 6 member, 5 member tetracyclic compound having several chiral centers, very complex structure, makes from very simple starting material. So, in your UG lab, whenever you want to make one organic synthesis, am I right? Diels order reaction, Friedel-Crafts alkylation, acetylation, you will be heating it, am I right? Sometime you stir it, heat it, then work up, purify by column chromatography, or sometime cool it minus 10 degree, minus 20, then purification, distillation, crystallization, am I right? Then you go to next step. But in nature, you do not have heating system, am I right? You do not have cooling system, you do not isolate anything, you do not recrystallize anything, but everything happens by its own. That is called biosynthesis. Okay. So, when nature makes natural product by biosynthesis, for some reason, if we want to make by ourselves, take it from nature, we are happy. So, you want to take sugar, sucrose is a nature product. You can isolate from sugar cane, very cheap, nice crystals, happy. For some reason it is not available, then you have to make it. So, that is chemical synthesis. If that molecule is optically active, studio chemistry comes in the picture, am I right? Optically active, immediately antenna will be activated. What is optically activated? Oh, something polarimeter, left handed, right handed, am I right? So, the compound what you synthesize, if it is optically active compound, then we call it asymmetric synthesis. So, what is optically active compound? All those things we will see, not that much basic, little bit higher level we will discuss in the chemistry. So, what do you understand now? If you take organic chemistry, so again we can divide into methodology, catalysis, bioorganic chemistry, carbohydrate, amino acids, peptides, okay, and total synthesis, making molecule with several steps, and like that there are several areas, transition metal catalyzed reactions, organocatalyzed reactions, organic catalyst. Okay, in that very few areas I have listed, and one is asymmetric synthesis, and that has 7.5% in this issue. Then you can understand it is somewhat common, not only important, commonly carried out research. Okay. So, that much you are understanding. So, in this 2 hours, already half an hour over, in this 1.5 hours, I will touch some of the topics. Okay, that is what I have listed here. So, first chirality, I told you for asymmetric synthesis basics is stereochemistry, and all your stereochemistry mostly focused on chirality, am I right? What is chirality, what is chiral compound, what is optically active compound. So, that is what we will be discussing. If a compound is chiral, it has major role when it acts as a medicine, drug, that is what I put it here. The medicine's activity, how it is going to affect, that is I am going to discuss again to tell you that how important the chirality or asymmetric synthesis, if not your stereochemistry. So, that is a way to start. Then importance of chiral molecules, okay. Then asymmetric synthesis. Asymmetric synthesis means making the molecule. Chiral molecules mean does not matter whether you made it or you isolated or taken from your friend's table, does not matter. If at all you have, that is the meaning. You go to pharmacy, take a compound, am I right? That is taking, am I right? Not in friend's table, pharmacist's table. Okay, you take it and use it. And third one, selectivity. So, you are talking about asymmetric synthesis in this course. I told you for asymmetric synthesis basics is stereochemistry. So, asymmetric synthesis means I told you synthesis of optically active compound. am I right? So, if you have optically active compound, then there will be two possibilities, enantiomers, am I right? Levorotatory, dextrorotatory. So, in that selectively you have to make one compound. So, you make a chiral compound, it has both the enantiomers plus minus equally 50-50. Is it going to optically active compound? It is a racemic, 50% clockwise, 50% anti-clockwise, and that will cancel each other. It is not optically active compound, am I right? If one is more, one is less, then it will be optically active compound, am I right? So, if one is more, one is less, that means selectively you make one as a major and one as a minor. That means you are talking about enhanced selective reactions, am I right? Selective. When you talk about selective, that is a topic. You are talking about, if you want to talk about selectivity in this 1.5 hours, we will talk about all kind of selectivity known in the chemistry because of your first year MSc you are completing, and also we will come to enhanced selective reactions. That means there are 3-4 types of selective reactions in chemistry or organic chemistry: chemoselective reactions, regioselective reactions, stereoselective reactions. Stereo means stereochemistry, am I right? So, that is related to this course. Again, stereoselective reactions you divide into enhanced selective, diastereoselective, am I right? And asymmetric synthesis related to enantioselective reactions. So, enantiomers mean chiral compound, selectively making, so selectivity, that is what the overall selectivity will be discussing. Then definition, what is asymmetric synthesis? What is the basics or basic principle of asymmetric synthesis? That also we will discuss. Again, this is BSc, MSc first year or third semester thing. First year generally you should have, Gleiden book has all the details. Okay, you can go and verify. And determination of optical purity. This is little bit higher level, your fourth semester course. Okay, how to determine optical purity. When you say optically active, am I right? It can be any kind of purity. 50-50 is racemic. 60-40, 20 to like 80, 90-10, am I right? Once you make it, how to determine the purity. So, that is the most important job in asymmetric synthesis. If we have a time, we will touch this topic. Then the final one, I mean optical purity and absolute configuration. We might have seen optically active compound is plus, minus, am I right? R compound, S compound. Okay. How to fix this R and S? Configurational nomenclature. This word you might have studied, am I right? Configurational nomenclature is a very difficult job. Used to be, now little bit easy. So, how to determine that we will also discuss if we have time. And finally, I will just take a compound called Taxol, very popular compound. You can Google it whenever you want. It is a very important medicine for cancer. So, history of developing a drug, how a compound became a cancer drug, how many years it took, what are the difficulties, that we will discuss at the end of the thing. Again, if I do not have time, few things in between I will skip, but this portion I will cover. Okay. After that, if at all I have time in today's lecture, I will spend 10 to 15 minutes what to do after your MSc. What are the possibilities in India, what are the possibilities abroad, PhD, postdoc, taking job, that all. If I do not have enough time today, then we will discuss on the last day, morning, when I am going to talk about catalysis, nano catalyst. That day I will talk in the last 15 minutes about that possibility. So many faculty will talk about that. Everybody's view will be different. Everybody's, I know something, other person may know other thing, am I right? You make a note of everything and you take whatever is best for you, am I right? So, that is the way it is. Okay. So, now we will talk about chirality versus drug activity. Okay. Now, you look at this compound thalidomide. Some of you should have heard this compound. If not, you should never ever forget this molecule name. Whenever say somebody thalidomide, immediately your antenna should be activated. Oh yes, I heard this compound. This is the problematic compound. Because of that only, there is a huge changes happened in the area of medicine. Okay. The whole, there is a word called chiral switching that we will see after few slides. Chiral switching happened just because of this molecule. Now look at this molecule, and this is having medicinal property. It is working against insomnia, cough, cold, headache. So this compound was marketed by West Germany in 1957, long ago, and other 50 countries by a chemical company called Gurenthal. I don't know how I pronounce because it's a German letter, you see it here, and the name what they gave is a Cantergent. That's the name they have given. So you know, when you want to take a compound to a medicine, it's a very expensive process. Today I realize, oh, this compound has some activity. Today I realize it will take minimum 10 years to become a drug in the pharmacy, minimum 10 years, not that easy. Also it needs roughly 15 to 16,000 crore rupees. For a compound to become medicine in the pharmacy, it needs 15 or 16,000 crore rupees. Can you or can I invest that much money? No. Can we wait for 10 years after investing? No. You are having 20,000 crore rupees, you are investing 15,000 crore rupees. After that, that medicine is not approved. Finally, all your 15,000 gone. Am I right? Even if you have 20,000 crore, you cannot invest unless otherwise you have a few hundred crore rupees. That is why the R&D in India, new medicines are not coming up, because you need huge investment other than scientific part. Okay. So now after everything, a medicine came in the picture. After everything, okay, then after started using, so thalidomide was used as a medicine to treat the early stage symptom of pregnancy. If a lady is carrying, she becomes pregnant, early stage of pregnancy, they used to have a giddiness, am I right, and vomiting sensation. For that, this compound was used. Very nice, huge investment, 50 countries, particularly West Germany, known to be one of the superior superpower in the technology, science and all. But after taking this medicine, see, it takes 10 months for the delivery, am I right? So after say 1 year or some time, they have realized that this compound has a serious side effect, so called teratogen. That means that causes abnormality in the baby, in the fetus. It creates a lot of side effect. So now you enter the word in Google, thalidomide effect, tragedy, something or thalidomide babies. This is the word you can, as you enter. Then you see lot of babies born without hands, without leg, without both hands and leg. You can see it here. A baby in the face, the defect. So after taking this thalidomide, a lot of side effect happened. So it took 2-3 years for them to realize, yes, somebody is going to doctor, they are prescribing something, then they are taking, and like that so many things. They will not realize why it happened, am I right? When baby is born, lot of babies are born, while born itself, birth itself, the kids passed away or without legs, all the things are happened. So by 1961, it affected more than 10,000 kids, and several people, kids died. So they didn't realize what happened. They didn't know. But what they realized, oh my God, if you take this compound as a medicine, it has a serious side effect on the baby. So stopped. They didn't know the reason. That's the point. Even that time, they didn't know the reason. So they stopped. Now you see at this thing. This is in. There's a person called Dr. Frances O. Kelsey. She's a MBBS doctor, physician in USA. Worked in a FDA, Food and Drug Administration of US. If you want to sell any compound drug medicine in US, the FDA has to give a permission. Like we have Indian Medical Council for Medicinal Research, okay, ICMR, equivalent body. And this compound is marketed in more than 50 countries, including West Germany. So when it goes to US, it should not be a problem, theoretically, am I right? But that time, I think one by a UK scientist, one paper was published saying that this thalidomide affects the human nerve system. So she asked to prove that it is not going to have any side effect. So I don't have any data. What I understand, they were not able to prove, and because of that she said no. She was a very new employee, joined a month back. She has to review and give the application. Already I told you the worth of pharmaceutical, everything, 10 years it takes, $2 billion, already marketed in 50 countries. But she was so young, new, but boldly said sorry. Okay. But after 1961, they realized that because of this Francis O. Kelsey, hundreds and thousands of babies are saved in US. Am I right? So one person, just imagine you are a new employee and already it's a drug, I told 2 billion whatnot and everything, but you say sorry, okay, in Germany, okay, let them sell, not in US, chalo chalo go. Okay, so that's a bold. So the country was so happy. So they gave her a president medal, that's called President's Award. It's a very big award in US, and she was allowed to work in FDA till age 90. Okay, work as long as you want, you can. And also they have started an award on her name, Dr. Francis O. Kelsey, Safety Excellent Award, in her recognition. The honesty, the hard work, am I right? Boldness, that is the award for that. Okay, this is all US story. Now come to India. So this is you can see it here, September 1, 2012. This is the news. One day I was reading newspaper, of course teaching stereochemistry, IIT Madras, so I know what is thalidomide. Normal people may not be knowing it, but this was the editorial page. It says German company that produced drug thalidomide, very sorry, 50 years later. This all I didn't know, that no textbook mentions about all those things, am I right? Now you can see here in Hindu editorial page, contagion drug maker apologies after 50 years. Thalidomide apology insufficient, that is a victim. Forget about that, come to the Tamil, Garan, local newspaper, it has written an editorial page. I was wondering, I know thalidomide because I am teaching the stereochemistry, or as a chemist you might have learned in the stereochemistry, but nobody knows, even most of you might have not heard so far, am I right? How a common man should know about that, and they have written editorial page. That means how much problem it might have created 50 years back. That is the message you have to understand. Okay. But the message here is they produce the medicine, they realize it has a side effect, without realizing they stopped, they didn't even say sorry, that is what it says, am I right? And they didn't give any compensation, nothing. But that is a second, we will not get into that. The take home message, they didn't know that why it had a side effect. Now we are chemists, we will go back and see why it had the side effect. Okay. So now look at this molecule. Is it chiral compound? Center, chirality, am I right? Chirality because of presence of asymmetric carbon, that is center chirality, stereo center, am I right? Chirality because of axis, symmetry axis, chiral axis, atropisomerism, you should have studied. Atropisomerism you have studied, no? You cannot say no, it is there in +2 itself. The tetra substituted biphenyl, it can be chiral if the rotation is restricted, am I right? So even without asymmetric carbon, a compound can be chiral. So that's all you might have seen, otherwise you will be studying it. But this is a center chirality. How many asymmetric carbon it has? 1. If it is having 1, then how many stereoisomers are possible? 2. If you have 2, 4. If you have 4, 8. So what is the formula? Okay. So according that there will be 2 stereoisomers. Both the stereoisomers will be enantiomers. Correct? Okay. So plus minus R and S. So that is what this compound can have 2 enantiomers. One is R, other one is S. So during 1950s and 60s, the scientists, chemists thought that, or they never thought that both the enantiomers of a racemic compound can have different medicinal property. They thought it should have same, but in reality, no, it is not the case. For example, here this R thalidomide is having medicinal property, whereas S thalidomide it is not acting as a medicine, it is almost acting as a poison. So, that is the message they learn after 30 years, not that time. So, but later on in 1998, FDA allowed thalidomide to use for the cancer treatment in USA, repurposing drug. You might have heard this word during COVID pandemic, that word you might have. So, now they are using it for cancer, but you have to make sure that it is not given to a pregnant lady. That is a, because cancer also is a deadly disease, you do not have anyway, you need some kind of treatment, otherwise anyway he will die, am I right? So, that is a way, so repurposing. But the take home message here, both the enantiomers of thalidomide are not equal in medicinal property, which they did not know that time. They thought everything will be same, good or bad. Okay. Not only that, later on people realized that if you have a chiral compound, it will have two enantiomers. Both enantiomers, initially they thought equal, but thalidomide said it may not be equal. Then you see some more example, ketamine S and R, this is having anesthetic property, where this one is hallucinogen property, two different property. Now see another molecule, naproxen, whereas one is anti-inflammatory agent, where other one is liver toxin. Completely one is poison, other one is medicine. Okay. Now you come to another molecule, minus physostigmine. Okay, this is a complex molecule. This is having a particular inhibitor of the cortex acetylcholine esterase. So here both the enantiomers are positive, both, but one enantiomer 700 times more active than other one. It's not another one is, it's not equal, different, both positive, but one is more than other one. Okay, now you take minus carbohydrate, anti-cancer agent, one is anti-cancer, other one is silent. So now putting everything together, what do you understand? Putting everything together, I make a new chiral compound, racemic, is going to have two enantiomers, both will be having same property or opposite property, or one is more, one is less, or one is active, one is non-active. It can be same, good, same, bad, one is good, one is bad, one is more, one is less, or one is active, one may be not active, nobody knows. It is your job to prove that yes, this is medicine, other one is also medicine. That is a very, very, very important phenomena introduced by FDA in 1988. So, when you make a chiral molecule, it will have two enantiomers. Okay. Initially people thought enantiomers will have same biological activity. No, it is not correct. Then thalidomide says no, it may have opposite property. Yes, but not always. Then one molecule says both, one is more, one is less. Yes. Some molecule says one is active, one is not active. It can be any kind. It depends on your molecule. If it is new molecule, you have to prove. And because of this, after 1961 thalidomide tragedy happened, am I right? After almost how many years? Close to 30 years, am I right? They brought a new rule saying that, okay, if you have a chiral molecule, better use single enantiomer, better. But everybody wants to be the topper, everybody wants, am I right? Is it possible? No. Making chiral molecule in enantiomerically pure form is not easy. If you want to make chiral molecule in enantiomerically pure form, you want now, am I right? So that is called asymmetric synthesis. Optically active compound, but single enantiomer, pure compound. So that is asymmetric synthesis. So, but it is not easy, but you are making only racemic compound, then what you have to do? You have to make sure that the other enantiomer is not having any side effect, the restrictions are increased. Okay, then you have to prove that no, it is not having any side effect. Of course, after 5 years again somebody may come and say that okay, I get some kind of side effect, then that all will come, but now it is more stringent. So this is the rule implemented by FDA in 1998. If you are using chiral molecule, better use single enantiomers, otherwise show that other one is not having any side effect. So that made lot of changes in pharmaceutical company. For example, this rule came in 1988. So in 1994, you see this some kind of new drugs introduced. 20% pure enantiomer, racemic compound 21% and no chiral, that is achiral compound 31% and some other details. Okay. From 94 to 97, just in 3 years, see how the market shift is happening. The 20% enantiomerically pure becomes 30%, increasing. Am I right? 21% racemic becomes 9. They don't want to use racemic compound now because problem. Am I right? Either go for enantiomerically pure compound chiral, otherwise go better achiral compound. So that's the way the market is getting shifted from racemic to enantiomerically pure. Okay, this is called, now you see it here, this is the details I want to give, and you can see it, yes, because of this shift the single enantiomer selling as a drug is increasing. Okay. So this phenomena is called chiral switching. I used this word in the first slide, am I right? So people started switching from using a racemic to enantiomerically pure. So this changed made lot of difference in the area of medicinal chemistry. Okay. And how big this market, how big? This we are talking about osmosis, this is very important, chiral molecule, drug activity, thalidomide. Okay man, what is the market size? That's very important, no? Am I right? So look at this data, it's all very old data taken from chemistry, chemical and engineering news 2000, it's all quite old data. Of course, after that one more thing, 2005 something data I have recovered, but what you understand here, this is the data from there. Now you can see here, annual sales of chiral drugs, a compound which is enantiomerically pure compound they are using, 133 billion in 2000 and 172 billion in 2005. Okay, that means 8.64 lakh crore rupees. Lakh crore, and this is 11.82 lakh crore. It's too much money, that much we understand, but we don't know what it means, am I right? I know 100, 200, 1 lakh, 2 lakh, 1 crore, 5 crore, I know what it is. Too big money now, we can't imagine. So I will make a comparison now. So Indian budget 2005, whole Indian Union budget, and budget always you will see two terms, income, expenditure. For us always expenditure is more, am I right? Okay, so this is expenditure. Indian budget 2004 to 3.48 lakh crore, whole India's budget. I am not talking about Tamil Nadu. 3.48 crore in 2005 expenditure, whereas same year the annual sales of chiral drug 11.82. At least how many fold? 3 plus fold. 3.5, am I right? Is it big market? Huge. You make small improvement, you will become billions of money, am I right? So that's the way. So it's a way, making enantiomerically pure compound is very, very important. And if you want to make it, you make it, we mankind in lab, that's called asymmetric synthesis. When nature makes natural product by biosynthesis. Okay. So when nature makes, then why should I make? We can ask, no, why should we make when nature makes? So obviously when it makes we take it, when it doesn't make, all of a sudden 5 years back there was a pandemic. Everybody was running to pillar to post to get a medicine. If somebody has developed a medicine for COVID, imagine, and he says it's 5 crore rupees, one tablet. There were so many people who are ready to pay 5 crore, am I right? If you have money, otherwise anyway it's okay, anyway, okay. That's the way it is. So demand is there. So there will be a demand. How much demand you have, this slide will tell you. This is the data in a book I have taken in 2000 if I understand correctly, and this is as on 1990 and that particular year for infectious disease, if I remember correctly, 1850 drugs were introduced in the market. Very old data. Okay, that's the data, but it will convey the message. Now the ratio may be different, but you see, out of 1850 medicines introduced in the market, 523 compounds natural product are semi-synthesized, slightly modified. Okay, whereas 1327 compounds are synthesized compound. We made it. The message is compound from nature is limited. You have to make more and more. Every day there is some disease, some problem, am I right? You have to make, this is the message you are getting. So now you take, if you take a natural product, out of 523, 6 compounds are achiral, no chiral center, whereas 517 compounds are chiral. So when nature makes a chiral compound, am I right? It is not worried about other thing, very simple. And out of 517 chiral compound, only 8 compound racemic, and all other compound 509 out of 523, 509 enantiomerically pure. When nature makes mostly enantiomerically pure compound, no enantiomer selective, okay, enantiomerically pure compound it makes. That is nature. I told you nature is great. We always inspire from the nature, very decent word, or we always copy from nature, normal word, am I right? Nature is great, am I right? It's a technology evolved for millions and billions of years. It's not joke, am I right? It's there for millions and billions of years. But when man make the compound, you see out of 1327 compounds, around 800 compounds achiral and 528 compounds chiral. So now here mostly chiral, here mostly majority achiral. So we have a problem in making chiral compound, and out of 528 only 61 compound enantiomerically pure, remaining all racemic. And when you want to use racemic compound, FDA has the problem because it has a side effect. So what is the take home message? Nature is great. Nature is great. It can make chiral compound than the achiral compound. Even that chiral compound mostly enantiomerically pure. When we make mostly achiral compound, if at all chiral, racemic compound. So if you make these racemic compound as enantiomerically pure, that is great, am I right? That is why I told you when we make the compound in optically active form, but when you want to use it as a medicine, you need optically pure compound. So we call it asymmetric synthesis. That is the need what you have to do it. So again another data, if you any drug you buy from the pharmacy, the top selling drugs, 50% compounds are sold as a single enantiomer. That is why it's in billions, am I right? And if at all you want to make it, if nature makes, you can take it, no problem. If you want to make it, then that is asymmetric synthesis. So asymmetric synthesis is the typical chemical synthesis where the product is going to be optically active and preferably single enantiomer. Okay, so that is the definition. Then how important the asymmetric synthesis? Before that, this is the definition. Okay, so what is asymmetric synthesis? I am telling asymmetric synthesis, but somebody will not use this word. There are several other similar words. Somebody may use the word enhanced selective synthesis. Somebody use the word chiral synthesis. Somebody may use stereoselective synthesis. Okay, depends on what type of reactions they are doing, what is their mindset. Am I right? This is all standardly used in the textbooks. And broadest definition for asymmetric synthesis: synthesis of optically active compound. I told you already a number of times. Am I right? After that, I think now onwards you may not forget. That is what we think, but after some time you will forget because other things you are learning. Okay, and possibly single enantiomer, enantiomerically pure, or selective synthesis of one enantiomer over other enantiomer. So selective synthesis, that is what I told, selectivity. Am I right? Of enantiomer. So that is a stereo part of stereochemistry. When you talk about enantiomer, then you should know diastereomer, am I right? So that is a part of the chiral compound. That is what, if we have time, we will discuss about that. So again, how important this area? So far, 2 Nobel Prizes were given to asymmetric synthesis. The first one is in 2001. You can see it here, Williams, Rogeri, Nayori and Sharpless. And the breakthrough happened in 1968, 1980, and Nobel Prize was given 2001. Minimum 21 years, here 30 plus years, am I right? So you have to take a message, make a breakthrough and wait for 20-30 years, should be with alive, like we are alive, am I right? Otherwise for you will not get Nobel Prize. So make the invention at early stage, am I right? So that make sure that you get that credit. Okay, and these are all details, you don't need to worry. And 2021 Nobel Prize. So the one Nobel Prize was given metal chiral complex, transition metal complex, rhodium, ruthenium, palladium. Okay, and 2021 is given for non-metal complexes, organic compound as a catalyst, there is organocatalyst. Okay, and that's the way. So you can details I am not going through. Okay, so what you have to understand now, the asymmetric synthesis means synthesis of optically active compound, preferably single enantiomer. Why you want to make single enantiomer? Because both enantiomers, if we have like not either 1:1 or any percentage, the other compound may create a problem. So FDA doesn't allow you to sell. Okay, so if you want to make single enantiomer or most major enantiomer, if it is available from nature, happily you take it. If it is not available from nature, you have to make it. But to make it, methodology may not be available. Am I right? If you come for PhD, then you will be developing one of the methodologies. And if it is successful, that's a great thing. Okay, research is all about developing new things. If you are in an industry, they want to make a molecule. If everything is available in the literature, they will follow the literature. Organic literature, JAG, scientific, nature. If it is not there, it's not there. You can understand, am I right? The technology to make an enantiomorphically pure compound is even today is not enough. It's not that any compound you can make an enantiomorphically pure. It's very difficult. So you have to make more and more. Am I right? 150 years back, no car. No car. Forget about India doesn't. No car. It was like came all 120, 30 years or 40 years back. But now everybody has a car, am I right? And if you see the history, started from 2-wheel, 3-wheel, 4-wheel, all kind of boxes, and slowly now, that's a development. Always it will happen. Initially there will be nothing, and slowly 100, 200, 300 years, everything will develop. That's the way it's going to happen. Okay.
SwayamPrabha, Digital India, Educated India.